So in this module, we'll talk about principal component analysis and its different interpretations. In this module, we look at one interpretation, and then in the rest of the module, some other interpretations. Okay. So the story ahead is going to be this. We'll talk about PCA and its interpretations. Okay. So now let's try to motivate PCA first. Consider the following data. Okay. In what dimension is this data? 2 dimensions. It's R2. Okay. And each point here is represented as its x coordinate and using its x coordinate and its y coordinate. Okay. Now it means that we are using x and y as the basis. Right? That's clear. That's the standard way that you would do. Right? Any data point you'll just represent using that basis. Now what if we choose a different basis? Okay. Let me give you one basis and then let me ask you some questions on this. Suppose we chose this basis. So in the previous modules we made a case for the x and y coordinate axis. There is nothing sacrosanct about it. You could use any basis. The only condition on the basis is that the vectors should be linearly independent, and in fact if they are orthonormal, it's even better, right? So now I've given you a different basis. Now what do you make any observation here? So they have all the points here have a very small component along the u2 axis, right? So now so for this point, right, if I consider this point, then this is the component along the u1 axis. So that's its u1 coordinate as akin to the x coordinate, and this is its u2 coordinate akin to the y coordinate. Okay, are the arrows clear here? Okay, so that means their u2 coordinate is very small, and it's also very small for all the data points, right? So it's almost as if there's some noise there. It's all within some epsilon. Now, so it seems that the data which you had actually represented in R2 can actually be represented in R1 by getting rid of this noisy dimension. Right? So if you had chosen a different basis, you realize that with just one dimension, you could have captured everything that was there in the data, and the other dimension was just adding noise. It was redundant. There's hardly any information there. Okay. So now, can you state this more formally? This was this intuition, but can you state it more formally in terms of things that you have learned in, say, probability for example? What is wrong with the direction u2? The spread of the data points along the u2 direction is very small. What does the spread mean? The variance, right? So we do not care about u2 because the variance in the data along this direction is very, very small. Okay, and in particular, right, if I were to build a classifier, then would u2 have any predictive power? Because along this dimension the points are indistinguishable. Okay. So think of it that you're trying to find out whether you have say 100 candidates and you want to decide whether they would be good basketball players or not, right? And quite naturally all the people that have shown up are say 6'2" inch, 6'3" inch and so on. They're in a very small height difference between them, and all of them are 6.2 is the average and very close. The spread is not much. So this feature is not going to help you decide whether this person is going to be a good basketball player or not. You'll have to rely on other features where the variance is more. For example, how many teams has he participated in the past? How many matches has he won as a team, as a member of some team and so on, right? So those you expect some spread to be there. All these 100 candidates might have different things, right? But if the height is the same for all of them, it's not going to be a good predictor. And that's exactly what is happening along the u2 direction. The points are almost indistinguishable there, okay? That's why it doesn't matter. So in general, given any data, now this was a simple case where the data was R2. I'm talking about the general case where the data is Rn, right? And you will find this situation in higher dimensions also. So you would not want to use that entire n-dimensional data where you know that there are some columns along which the variance is very small. So you want to represent the data with fewer dimensions such that the data has high variance along those dimensions, okay? Now let me just clear a confusion here, right? So I am not saying that take your n-dimensional data, okay, find the variance across each of these dimensions and then throw away the columns which have the lowest dimension. In this particular example, if you had done this, what would happen? Could you have done that? Think of the original dimensions x and y. Along these two dimensions, there is enough variance in the data, right? The x coordinates vary from here to here, and the y coordinates also vary from this point right up to that point, right? So there is enough spread in the x and y coordinates. So in your original data, I'm not saying that look at each column and see if there is no variance along that column, then throw it away. That won't work because you might end up with a situation that there is enough variance across each of these dimensions. It's just that when you look at the data from a different angle, that means you project it onto a different basis, this becomes clear, right? So you see the difference, right? That's not the same. These two things are different operations. So what I'm looking at is projecting the data to a different basis. That's exactly what I did with U1 and U2. And then some things became clear about the data. Now this projection along a different basis, I would be interested in doing that only if I can get rid of the number of dimensions, right? If now I had already had one basis where I had n dimensions, now if the new basis is also going to be that all these new n dimensions that I've come up with are important, then you're not gaining much, right? You still have this high dimensional data. But you would like to project it in a way that you get rid of the lower variance dimensions. So you might project it onto n dimensions, but you want to rank these dimensions according to variance and then throw away some of these dimensions. Is that clear? Is the objective clear? Okay, fine. Is that all that we care about? N dimensions, project to a new basis, and throw away the k dimensions which have less variance. Is that all? What else would you want? People who have done the MLPR course? No, I wouldn't. So I'm not going to classification or anything. I just want a better representation of the data at this point. I'm not really thinking about what I want to do with the data, right? You're talking in terms of classification. And we have already seen even if the data is not linearly separable, we have solutions for dealing with it. So that's not a critical point, okay? So there's something else that we're interested in, and let's look at that, okay? Now consider this data. I have three-dimensional data, okay? Do you find something odd about this data? Y and Z are highly correlated, right? Do you want these dimensions? Can you think of in practice such dimensions occurring? Height in centimeter and height in inches. Someone would have just given you data, right? Or if you take the credit card fraud detection case, right? Someone would give you the salary and they would also give you the income tax. Now these two are highly correlated, right? So then you don't really care. If you have one, you could probably almost with certainty predict the other, right? Modulus some rules, right? Because you get some tax exemptions and all that, but still. So you can have this in practice, right? Even in our oil mining case, your salinity, pressure, density, those things could be related, right? So Z is not adding any new information beyond what Y is adding. So the two columns are highly correlated. So actually, yeah, this is the formula for correlation. All of you know this? Anyone who does not know this formula? Good. So nothing is a stupid question, right? So you can always ask. So Y hat is the mean of this column, okay? Oh, sorry, Y bar. Z bar is the mean of this column. And this is how you compute correlation. This is just the formula, okay? So from every entry, you subtract the mean, okay? So this is known as centering the data. So if you do this, what would the mean of the new data be? 0, right? So that's why it's called centering the data, okay? So you'll have 0 mean, and you, so what is the intuition behind this formula? Does anyone know? Okay, can you even tell me? So this is a summation, okay? So this quantity is going to be high if the summation is high. It's a summation of some n terms. Now these terms could be positive or negative. If all the terms are positive, what would happen to the sum? It would be high. If there are some terms which are negative, it would be low. Now when would all the terms be positive? Whenever Y is above the mean, Z is also above the mean, right? Therefore this quantity is positive, this quantity is positive. Whenever both are below the mean, again the product would be positive. But when one is above the mean, the other is below the mean, then there is something wrong happening there, right? And in that case, you will have a negative term, right? So you get the intuition? Okay, fine. So for more details, of course, you can refer your other textbooks and so on, but this is just the intuition, okay? An important step here is to zero mean the data, right? We are computing the, subtracting the mean of the data, okay? Another way of saying this is that the column Z is actually linearly dependent on Y. Okay, it's almost linearly dependent. I of course have some noise, 2.1, 0.76 and so on, but it's largely linearly dependent. I can write Z as some C times X. Okay, fine. So now, can you tell me the refined goals that we have? We are interested in representing the data using fewer dimensions such that, remember that when I say fewer dimensions, I mean a new set of dimensions, right? It's not throwing away dimensions from the current data. We are looking for a new set of dimensions. What are the conditions that we want from these new set of dimensions? One, there should be high variance along these dimensions, the new dimensions, and the dimensions are linearly independent or uncorrelated. Okay, fine. And even better, of course, if they are orthogonal. Why? Because we are looking for a new dash basis, and the most convenient basis is orthogonal basis. Okay, fine. So now let's assume someone has given us this new basis. Okay, and let us call this P1, P2, Pn. So instead of this x, y, z, and so on, someone has given us this new basis. Eventually, we'll of course figure out how to find the basis, but let's assume that someone has given this new basis, right? And they are both linearly independent, and actually, it's redundant actually. So yeah, this example of a redundant feature. As such, n orthonormal vectors is sufficient. They are linearly independent. Okay. Let P be an n cross n matrix such that P1, P2, Pn are the columns of P. Right? Same thing as we had put the eigenvectors in a column, and probably I've unknowingly given out the solution. But okay, and let x1 to xm be the m data points given to us. Okay, so we are given this data as usual. We have this X matrix. Each one of them belongs to Rn, and we have m such data points. Right? That's the standard thing that we are operating on, and we always write this as a matrix. Okay, and we have already done the data is zero mean and unit variance. Actually, unit variance is not required, but the data is zero mean. Fine. That we'll. I'm going to deal with covariance. So unit variance is not required. So the data is zero mean is what I'm going to assume. But what if the data is not zero mean? I can always make it zero mean, right? So just remember, this is an important trick that you will always have to use whenever you're doing any large scale machine learning. So whenever you're participating in Kaggle competitions, almost the first thing that you do is standardize the data. That means make it zero mean and unit variance. So why is that important? Right, scaling issues won't be there, right? So if I have something in centimeters and some other unit in kilometers, right? Now remember that always you're doing somewhere this linear operation W transpose X. You might add a non-linearity on top of that. But now if your Xi dimensions, some of them are in the range of 0 to 10,000, some of them are in the range 0 to 10, right? Then there is some abnormality here, right? Some dimensions are winning in terms of their magnitude and some dimensions are losing out, right? That's why you always make it unit variance and you also make it zero mean. You center the data. Okay, so we'll assume this, and if we all understand if the data is already not zero mean and unit variance, we can always make it zero mean and unit variance. Just scale it and make it centered. Okay. Now we want to represent each xi, right? So xi is one of these data points that we had. That means one of the rows of our matrix. Okay, and we want to write it as a linear combination of this new basis. So if you have any basis, any vector, you can write it as a linear combination of that basis. Is that fine? So far it's okay? Okay. Now, for an orthonormal basis, we know that we can compute these alphas just by taking a dot product of the vector with the dimension. Okay, I'm just repeating some of the things. Fine. So now let's see what this means. For one of the dimensions, this is my data point xi, which I want to transform. Okay. For one of the dimensions, I just had to take the dot product with that dimension. And this will give me how many values? One value. That means the coordinate along P1. I want to do it for all the n of them. I can write it as this vector matrix multiplication, right? What's the dimension of this? N cross 1. How many of you get that? Okay. So this is, oh, not many. Why? 1 cross n. Okay, fine. That's fine. Yeah, how many of you get this? Okay, fine. Yeah, so this will give me all the n alphas. Is that clear? For this data point. Okay, so it will give me alpha I 1 to alpha I. Is it okay? Now, I want to do this for the entire data, right? So I've done it for x1. I also want it to be done for x2 and all the way up to xm. For each of these, I would have such an operation where I have a vector multiplied by this matrix. If I just stack all these vectors, I get back my matrix X, and the whole operation I can write as X into P. Okay, is that clear to everyone? Okay, what's the dimension of X into P? M cross n, right? So for all the m data points, I have alpha 1 to alpha n. Is that clear? Anyone who does not understand this? Okay, fine. So X hat is the matrix of the transformed points. Is that clear? I have now the new coordinates. Instead of the original coordinates according to the coordinate axis, I have the new coordinates in this matrix. Okay. Now I'll just go through some very simple theorems, or rather results, and I'll not prove them. You can prove them on your own, or the proof is there in the slides. You can look at it later on, right? So if X is a matrix such that its columns have 0 mean, and if X hat is equal to XP, then the columns of X hat will also have 0 mean. Is this obvious to most of you? Not really, is it? How many of you think it's obvious? Okay, then let me just go over the proof. So for any matrix A, 1 transpose A, right? So that means you have this vector, no, this is a vector or a matrix? Yeah, this is a vector, right? So I have a vector of n ones. So 1, this is nothing but a vector of n ones. So what is this product actually going to give me? It will give me a vector containing n elements. What is each element? Sum of that column, right? Is this fine? Okay, this is very obvious to see from, if I have this, suppose I have 2, 3, 1 and 3, 6, 7, okay? And then of course the corresponding, so if I do this multiplication, I'll get a 2-dimensional output which would be just 7 and 16, right? So that's just the sum of that column, okay? This is fine. Oh, sorry. So now we have this X hat, that's the transform matrix. Now let's see if I do this operation X hat, what happens. I can write it as this, I can club it as this. What is this? It will be all zeros, because the original matrix was mean 0. That means the sum of the elements of all the columns, each column independently was 0. That was, this is going to be a 0 vector. So 0 vector multiplied by any matrix is going to be 0. Now is it obvious? I hope this is obvious. X transpose X is a symmetric matrix. Okay, and I still have the proof for that. Okay. Now if X is a matrix whose columns are 0 mean, then a matrix sigma, which I'm going to call as the covariance matrix, which is given by this, is actually the covariance matrix. How many of you agree with this? How many of you have seen the covariance matrix before? Okay, good. So all of you agree that this is the covariance matrix? If you don't, please raise your hands. If you don't, you will not understand the rest of the stuff. Okay, now you have to be given the right incentive. Okay. So let C be the covariance matrix of X. Now what is a covariance matrix actually? First of all, tell me that. If I say that I have an n cross n matrix X, okay, let me not make it n cross m, let me make it m cross n, okay. What does the covariance matrix actually capture? What is the dimension of the covariance matrix first of all? N cross n, okay. And what does each entry of the covariance matrix capture? The covariance between the ith column and the jth column. So the entry ij of the covariance matrix captures the covariance between the ith column and the jth column. Is that fine? Now what's the formula for covariance? Suppose I give you 2 columns, right? Let's see, I give you x11, x12, x13 and x21, x22, x23. Can you give me a formula? And of course I'll go up to k, or rather m, right? So what's the formula? Summation equal to 1 to m mu1 mu2. Anything missing? By m. Anything else in the denominator? No? Is it fine? Okay. So and what is mu1? Mu1 is just an average of this. Okay. So this is the covariance formula. Now if the mu's are 0, then what does this boil down to? x1i into x2i. What is this quantity actually? This is the dot product between the ith column and the jth column. Okay? Fine? Okay. Now that's pretty much the explanation, right? So now theCijth entry is supposed to be given by this formula. If the means are 0, you are just left with this formula. And this is nothing but the dot product between the ith row and the jth, the ith column and the jth column. Okay? Is that fine? Okay. And now if you write it as a matrix, then you can just say that it's the ijth entry of the X transpose X matrix. Everyone gets this? No one has any confusion? The people who raise their hands? Fine? Okay. Good. So now, okay, so now this is where we are so far, that we have assumed that someone has given us these dimensions P1 to Pn, which we have put in the matrix P, right? And we have also made a case that X into P, which is what I have written here, actually is just a projection of the original data onto this new basis, right? Everyone gets that? Okay. And I'm calling that new projection, or the new result that I get, as X hat. So that's what my transformed data is. What is missing here? We don't know what P is, right? I'm assuming someone has given me that P. Now I need to figure out what is the P here, okay? Now, using the previous definition, we get that this is the covariance matrix of the transformed data, okay? So let's just write that. Is this fine? Is this fine? What is this? Covariance matrix of the original data. Okay, so I'll just write it as sigma. Fine? Okay. Now each cell ij of the covariance matrix stores the covariance between columns I and j of X hat, where X hat is the transformed data. What is the property that you want to hold? I'll give you two conditions, or rather I'll give you only one condition for now. When I is not equal to j, 0. Okay. So what should the covariance matrix look like? Remember that this is, what is this? This is the covariance matrix of the transformed data, right? That's what I started with, right? This is the covariance matrix of the transformed data. What do I want this covariance matrix to look like? A diagonal matrix, okay? Because I want every non-diagonal element to be 0, right? And at this point I'm not telling you what I want the diagonal elements to be. I'm just telling you I don't want them to be 0. Because if it's 0, what would that mean? That's the variance, right? If you take the along the diagonal, what you get is the variance. It's okay if it's not clear right now, we'll return back to that. Right now we just know that the off diagonal elements are the covariance between the ith and jth column, and we want that to be 0. So we want this condition to hold. Now this is something very new that you have never seen in this course before. You have actually not seen in this course before. Okay. Have you seen this or not? Okay, thank God. Fine. So what is this? The diagonalization of which matrix? This matrix, right? And what was this matrix? It was X transpose X. Is this clear? So what's the solution? All roads always lead to eigenvectors, right? So we want P transpose sigma P to be a diagonal matrix, and we know which are the set of vectors which I put in P such that they will diagonalize sigma. Eigenvectors of X transpose X, right? Oh wait, why did I put this? It's the matrix of the eigenvectors, right? So, okay, it's a matrix of the eigenvectors of X transpose X. So now have we finished it? Do we know principal component analysis now? So we started with the intuition that we wanted to transform the data. Okay, I cannot stress enough that we want to transform the data, not chop off dimensions from the existing data. Okay, that means we need to project the data to a new basis. And we had a couple of conditions. The variance should be high and the covariance should be 0. We have satisfied one condition, which is the covariance is 0. And we arrived at a solution which says that the eigenvectors forms the basis that you should project on, so that the covariance would be 0. Okay, so we have a solution. We know exactly which basis to use to represent the data. Okay, so that the covariance condition is satisfied. What about the variance? Did we do anything about the variance? Okay, so we'll come back to that. Okay, fine. Why is this a good basis? What is a good basis? The best basis? Orthogonal, right? Because the eigenvalues of X transpose X are linearly independent. That's okay, and they are also orthogonal because X transpose X is a dash matrix. Okay, good. Real symmetric. Okay, good. Okay, so this method is called the principal component analysis for transforming the data to a new basis, and where the dimensions are non-redundant because they have low covariance, and not noisy because they have high variance. The second part I have not proved, right? And I'll get to that at some point. Fine? Okay. No, that's what we saw, right? No, what's it? I didn't get that. Okay. Now in practice, how many eigenvectors would you have? N eigenvectors. Do you want to keep all of them? Which ones will you throw away? The low variance. Okay. And now in the next interpretation, actually we'll try to see what is the what happens when you throw away the least important dimensions, right? What do you mean by the least important dimensions, okay?